So first comment, go easy. Today please go easy on me. It's 5 a.m. here. So it's my first time giving a lecture at 5 a.m. It's exciting. Some people already sent me a bunch of questions over email on various subjects that this lecture's touched, which I haven't responded to yet, but I'll respond promptly. In any case, my email address is just that. And if you want to talk about anything, just send me an email, and I usually respond quickly. That's comment number 1. Comment number 2 is, before I continue, I'm going to continue from something that I already mentioned yesterday, but we'll just build a little bit more on that comment, because there were some questions after the lecture yesterday that prompted me to give a little bit more details, and it will be important for today's discussions. So are there any questions that we should discuss before I start? Anything that came up between then and now? Yes?
The last example we doing, is it true for only 2 plus 1 dimension, or is it for any dimension? Invariant transition theory.
Yes.
It goes true for any dimension.
No, this is always in we use this epsilon mu nu rho, a mu d nu a rho, right? So this is tailored to 2 plus 1, because you have the tensor here. There are generalizations of this to higher dimensions. Well, there are many generalizations of the notion of topological filter to higher dimensions. But this particular class of examples is in 2 plus 1 dimensions. Any other questions? Okay. So yesterday we discussed this surprising idea that this theory has no local propagating degrees of freedom. But still the vacuum has some sort of hidden topological order, robust topological order. And you can try to think of many ways to demonstrate that the vacuum of this theory is non-trivial. People have done many, many things to show that. One thing you can do is to try to compute the ground states on curved manifolds with topology. I mentioned that you can try to compute the wave function of the ground state. The simplest thing is to just take infinite space and put probe particles and show that there is an Aharonov-Bohm phase when you drag them across around each other, and that shows that there is something in the vacuum, some hidden, you could say, long-range forces, but they're not really forces. They're not carried by degrees of freedom. They're just topological forces, hidden long-range topological forces that lead to this Aharonov-Bohm phases. And one additional thing that we mentioned yesterday briefly was that this theory admits no local operators whatsoever. That just hammers this point that there are no local degrees of freedom. And in fact, I wanted to explain a little bit better why there are no monopole operators. I mentioned it yesterday, but I wanted to explain it a little bit more precisely, because today that will be important. So the equation of motion of this Chern-Simons action set the field strengths to 0 everywhere. Of course, if there are sources, as we discussed, then the field strength is not 0. There are solenoids that are stuck on these particles, magnetic field lines that are stuck to these particles. But in the absence of sources, the electric and magnetic fields have to identically vanish everywhere. And in particular, that means that you really cannot construct local gauge invariant operators out of the gauge field. F mu and any combination of F mu would vanish. So you cannot measure any local fields. Then there is the question of what about monopole operators? We define these monopole operators, and I want to explain a little bit more completely why they don't exist in this theory. So I'll give you a basic explanation, which is actually sufficient for this course. So remember that the monopole operators were defined by taking a point in space. So how would we define mx, m1x, okay? The basic monopole operator. We would take the point x, remove some neighborhood of this point. We're now in Euclidean space. We define them in Euclidean space. So the neighborhood of this point is like a three-dimensional ball. The boundary of this neighborhood is a two-sphere. And so we remove this point, this three-dimensional ball, and on the boundary of this three-dimensional ball, we declare that the gauge field must have non-zero flux, which is given by 2 pi times 1. So it's the basic monopole operator. It's the fundamental Dirac quantization on a two-sphere. And this S2 is centered at x. So this is the small S2 of radius epsilon that is centered at x. That's how we define monopole operators, through these boundary conditions. Of course, then we sort of have some sort, we have sources. So f mu is no longer everywhere 0. So this is like a source for the Bianchi identity. So in the presence of monopoles, this no longer exactly vanishes. The Bianchi identity now has a delta function at x. Well, it's more convenient to call this x naught. And then this delta function would be x minus x naught. Okay, so this is like a source for the Bianchi identity. So that's how we define monopole operators. A source for the, okay. Now, in the presence, so that's how we define them in general gauge theory. That's how they're always defined. However, sometimes this definition leads to operators that may not be gauge invariant. So the question is whether this construction is gauge invariant. In the examples that we studied in the previous sessions, these were gauge invariant operators, like in pure Yang-Mills theory. Pure Maxwell theory, these were gauge invariant operators that were in fact dual to the exponent of that sigma scalar. But here, because of the Chern-Simons interaction, because of this interaction ADA, they're actually not gauge invariant, these operators. So we should not discuss them. They don't exist really. And the reason is that one qualitative way of saying that is just think about this Lagrangian as k over 4 pi times integral of A wedge f. Okay. Now, so from now you can see this following thing. You can imagine that, well, A wedge f is like we can put A in the radial direction, and f can be with indices that are on the two-sphere. And since f on the two-sphere satisfies this looks qualitatively like an integral of A. Just write it down a little bit more clearly. So we write it like that. Let's now study the gauge variation. That will be a little bit easier. So what is the gauge variation? The gauge variation of this action, you remember we had a total derivative. So the gauge variation of the Chern-Simons action was given by an integral of the derivative of, it was given by omega df plus a total derivative. And when we discussed this equation before, we set everything to 0 because this satisfies the Bianchi identity. This is total derivative, an integral over total derivative. But now, in the presence of monopole operators, this has a delta function. And so you pick up a piece which looks like the gauge variation at the location of the monopole operator. from this piece. So you just integrate against the delta function and you find this thing, and some k. So when you follow the normalizations carefully, there is some k here because of this k. So what that means is that this local operator now does not transform gauge invariant, is not gauge invariant. Local operators, let's say in U1 gauge theory, this operator is not gauge invariant. What's his gauge variation? The gauge variation of this guy is given by omega times its charge times phi. So from this kind of argument, one concludes the following general thing that's always true: that in U1 level K, Chern-Simons theory, the monopole operator M of X has charge K, which is an integer, under U1 gauge symmetry. Under U1 gauge symmetry. So it's not gauge invariant, and that's why we don't consider this operator as a local operator. Now, notice that if you have some additional matter fields, like scalars or fermions, then you can multiply M by those scalars and fermions to make it gauge invariant, to cancel this gauge charge. And this will be an important construction soon. That when we have additional propagating degrees of freedom, the monopole operator would become physical because you could multiply it by various things. But in this approximation that we throw away all the massive excitations, there is nothing to multiply it by, so the operator just doesn't exist. This is a comment about yesterday that will be important for some things that we'll do today. Any questions? Okay. Yes? Of what? Yeah, M is the fundamental monopole, and that will have charge K. The monopole with n units of monopole charge will have charge nk. So you're asking, are there monopoles with gauge charge 1, right? That's what you asked? Yeah. So Mn will have charge nk, and n can be positive or negative. Yeah, you can. That's a great point. So you could say, let's take M1 and multiply by M minus 1. That's gauge invariant, right? But how do you convince yourself that this is a non-trivial local operator? In fact, in this Chern-Simons theory, this is the same as the unit operator, which is the only operator that exists anyway. Yeah. So by taking products of these operators, you can only get the unit operator. Indigo, that's a good point. Yes?
Can we define Wilson loops in this theory?
Yes. I have not mentioned this perspective, but in fact, everything we did yesterday was about that. We discussed probe particles. You remember our picture was that we had this little pudding cake with little points. What are these points? What were they? They were points where the charge density was delta x minus xi, and we summed over I, right? What is this? How do we mathematically discuss this thing? That's the Wilson loop, right? How do you see that this is a Wilson loop? This is a Wilson loop that's extended in time. Wilson loops describe the trajectories, world line trajectories of heavy particles. And that's exactly what we did yesterday. So if you want, I'll spend 1 minute explaining that what we did yesterday was all about the algebra of Wilson loops in this theory. So if you have A mu, J mu, and you decide to take J mu to be equal to this, to a sum over delta functions, so that means that J0 is a sum over delta functions. So this becomes integral of A mu, sum over delta functions in space. These are delta functions in space. And this has to be A0 now. And we integrate over time and space, right? I'm just expanding this term. So now we can integrate in space, and we get a bunch of integrals. So in time times, we get a bunch of integrals in time. This is if you go back to the action, you put an exponent, put an exponent, put an exponent. This is just a product of Wilson loops, which are extended in time. When we discuss the response of the system to probe particles, what we did essentially was to put time-like Wilson loops. Another thing that we did yesterday was to consider this little particle, and we discussed this trajectory around it. But I drew this trajectory in space, but actually it happens in time, right? We slowly drag the particle. So this describes a space-time diagram of Wilson loops that braid each other. Let me try to draw it in space-time. So this whole Aharonov-Bohm phase is nothing but a braid of two Wilson loops. So Aharonov-Bohm is just a braid of two Wilson loops. Let's try to draw this diagram in space. So we have one Wilson line that's just sitting, that's in time. And another one is winding around it. So it comes like this, and then it goes like this. That's the process of dragging something 300 degrees. You see? That's called the braid. And this is equal to exponent of I, the Aharonov-Bohm phase. That's exactly what we did yesterday. So you can reformulate what I said yesterday about Chern-Simons theory in a very abstract, if you want to be a little bit more abstract. There are no local operators. They all vanish. But instead, there are Wilson loops. And the Wilson loops turn out to have non-trivial braid algebra. They give a non-trivial representation of the braiding algebra. You can also think about it a little bit even more sophisticated. Instead of doing this, you can just do that. It's the same. And then you can think about it as a link. So, like this. You can think about it as a link. It's the same, because you just close it at infinity. So the Aharonov-Bohm phase can also be thought of as a linking invariant instead of a braid. It's the same thing. Also, this link invariance.
So we can link everything to the framing anomaly?
So no. So there are many things that we said yesterday should be reformulated with Wilson loops. That's a more correct mathematical way of saying it. And these Wilson loops satisfy various funny relations that if you link them, then you get a phase. If you don't link them, there is no phase. You mentioned the framing anomaly. That has nothing to do with that. Any questions? Yes?
Excuse me, I would like to ask you, if we present a monopole operator like the exponential of the subdual of the dual photon, that identity looks like real.
So in this duality with the, let me mention that again. I'm not rushing to get somewhere. It's okay to. You remember that to prove that this theory is dual to just the superfluid phase, we started from f mu squared, we did some manipulation, and we got to d sigma squared. In the presence of the Chern-Simons term, there is no such thing. So actually, this whole idea is just wrong when there is Chern-Simons. There is no connection to sigma when there is Chern-Simons. Why? You know it from the final answer. In Chern-Simons, the spectrum of the theory, which we discussed yesterday, was one massive spin 1 particle. There's no way it will come out of such a duality. This duality gives maybe a massive spin 0 particle, like when you add monopole operators, but it's never going to give you a massive spin 1 particle. So this just doesn't apply.
But my question is, then how can you sketch at least the proof of that identity? And is always true? I mean, given whatever...
You are asking about this?
Yes, exactly. Given whatever theory of monopole?
So the sketch of the proof of this identity is the following. The monopole operators have some monopole number, which is this n. And this so there is a U1 magnetic symmetry, and these monopole operators would like to transform under the U1 magnetic symmetry. All the operators that do not transform under the U1 magnetic symmetry, they must be made out of operators like f mu. That's the sketch of the argument. But we argue that there are no such things. The only operator all the operators that do not carry magnetic U1 symmetry, they're like polynomials in F mu, and maybe the fields, but there are no such things here. They all vanish identically, except for the unit operator. So therefore, it must be just the unit operator. There is no such thing as on shell. When we write operator relations, they're always on shell. On shell is the question of on shell versus off shell is an artifact of perturbation theory. When we write operator equations, they're always on shell. Any other questions? Okay, so if you, I just wanted to mention a little bit, maybe some students here are a little bit more advanced or want to go a little bit deeper. I want to make a few comments about this. So far we've been discussing abelian Chern-Simons theory, and it's abelian in the following sense, that if you took two Wilson loops, let's say of charge Q1, this is a probe particle of charge Qi, and this is a probe particle of Qj. When you make them close by, you just arrange them to come together, you can replace them with one effective Wilson line of charge Qi plus Qj. And that's, of course, no mystery. It's just the fact that these things are abelian, and you can just exponentiate and add them up. This is called an abelian fusion. Abelian fusion. In more general Chern-Simons theories, the fusion could be non-abelian. And when the fusion is non-abelian, there is also an interesting constraints on the possible braiding matrices and fusion matrices. So in general, there is a set of axioms that you can draw with pictures like that. Like what are the allowed braidings, what are the allowed fusions, what happens if you fuse this and that first, and then, so there are diagrams like this. You could fuse this and that first and compare to this, or maybe you could fuse this and that first, and then this guy would come at the end, right? So you could change the order of the fusion. Let's say you fuse that and that first, and then this comes at the end. So there are various relations on what these axioms that these pictures must satisfy. And if you want to learn about it mathematically, the correct framework is called the modular tensor category. So that's a mathematical formulation of all the axioms that the Wilson lines have to satisfy. And this is like the starting point to a classification of all the possible topological theories. Okay. Okay, let's get back to the next thing I wanted to mention. The next thing has, at first sight, nothing to do with this course, but you will see that it turns out to be very important for the next topic, and it's just a reminder of something that you might know. It's a reminder about something that you might know from your coursework. This is called, I think, this apparently was first discovered by Dirac, that's what I'm told. But I think mostly people attribute it to Wu and Yang. There is a nice paper by Wu and Yang about it, but apparently Dirac did it before. So it's an exotic, it's a somewhat exotic fact that's good to know. So suppose you have a magnetic monopole, so with some strengths n, you can think in 3 + 1 dimensions, or just it's going to be static. So let's do 3 space dimensions, 3 dimensions, 3 Euclidean dimensions. So suppose you have a static magnetic monopole, then the magnetic field that it radiates is just n times r over r squared. That's the magnetic field that this monopole gives, right? So there's a magnetic field that goes outside like this. Now, you can ask, what happens if I put an electric charge E? Let's say electric charge Q here. Q is an integer. The electric charge also radiates some electric field. So there is some electric field. In the electric charge, there is some electric field, right? So now we have also some electric fields in the business. When you have both electric and magnetic fields in any electromagnetic system, there is an intrinsic angular momentum that is stored in the electromagnetic field. So we have electric fields and magnetic fields. The angular momentum in the electromagnetic field that is stored in the electromagnetic field, that's from, maybe you remember it from undergrad, is E cross B. So you need to integrate this over x. So to compute the angular momentum, what did I do? The angular momentum is basically E cross B. I think I'm confused about the x, but let's not get it. So if there is both electric and magnetic fields, then the angular momentum is given by such a formula. Does that look familiar? Yeah. And a very interesting fact is that in such a situation, the electromagnetic field is Qn over 2. So the angular momentum that's stored in the system is Qn over 2. And in particular, if you set Q equals n equals 1, the angular momentum is a half. This leads to the famous fact that if you take a magnetic monopole, which is bosonic, you take a boson magnetic monopole, and you take a boson electric field, electric particle with electric charge 1, some bosonic electric particle of charge 1. So this is also boson, and they form some. They could be in some bound state or something. It doesn't matter. Then this system is a composite fermion. So this composite system is a fermion. So the bound state of two bosonic particles can actually be a fermion. Okay. So let me just write it. Bound state of two bosons can be a fermion. That's a shocking fact at first, but the resolution is that it's all stored in the electromagnetic field. You can ask if this violates spin statistics. There is a very interesting question whether this violates spin statistics. You can imagine another such bound state of two bosons, where this is a magnetic monopole and this is some charged electric particle. Since this is a fermion and this is a fermion, when we move such two things around each other, we should get a phase, Fermi statistics. But you could say that this makes no sense, since each particle individually is a boson. So there is some sort of tension in this picture, and there is a very beautiful paper from 't Hooft, Hasenfratz, Wu Yang, and then there is another paper that discusses this exact point by Goldhaber. So you should look at the paper by Alfred Goldhaber from the 70s, which discusses exactly this point and explains why it's consistent with Fermi statistics. So it's possible for two bosons to bound to a fermion. Counterintuitively, but it's possible. Okay? It's just a small reminder about a physical fact that you may have seen. Are there any questions about it? Yeah, they differ by some x that one needs to be multiplied by x to get from one to the other. You need to multiply by x. I forgot who multiplies x where, but both of them have E and B. In one of them, you need to multiply by an additional x. Okay, so now we move to our main subject. We'll discuss now an interesting example that is important in the context of the quantum Hall effect and several other applications that involves all these ingredients, topological order, this phenomenon, and many things that we discussed. So the theory that we're going to discuss now has a gauge field and a Chern-Simons term, but at level 1. So k equals 1. You remember that I mentioned this as a special case. This we already analyzed. We know everything about this model. So we discussed it yesterday. But now we'll add dynamical massive matter fields. So we'll add a massive complex scalar with charge 1. With charge 1 under the gauge symmetry. So phi is a charge 1 particle. This is a very interesting system that combines many things we've seen. We've discussed this model separately. We discussed these two combined terms. We discussed the already charged particles without Chern-Simons terms before. Now this combines many ingredients together. Phi is a charge 1 particle. And it's very, very important that the level of the Chern-Simons term is 1. What I'm going to say is only true about that particular model. If you start changing the level, you'll get completely different things. And there is a huge amount of literature analyzing what happens when the level is 2, 3, 100, infinity. Okay. So, but here we're just doing Chern-Simons level 1. So that's the model that we want to study. And the method of attacking this model would be like before. We'll just study what we can and try to make an informed guess. And the answer will be very surprising at the end. That's the idea. So the method of trying to understand the dynamics of this model will be to draw the same picture again and analyze it in different limits, which is the fun part. So the easiest limit is, both limits are actually very interesting in this model. But let's start from huge positive m squared. Let's start from huge positive m squared. So again, with the audience, what should we do in that case? When m squared is huge and positive. Right, so what is the Diplo energy theory? Right, so the Diplo energy theory, low energy, is just 1 over 4 pi a dA. That's U1, level 1, Chern-Simons theory. This theory has no excitation, right? This theory has no excitations. And how many anyons has it got? 2, because when k is odd, I said there are 2k. So what are the 2 anyons? One is a trivial anyon that doesn't braid. Maybe that's why you said 1. You didn't count the trivial one. The one is trivial, it's just the unit operator. It doesn't braid. And then there's another anyon of spin. The spin was q squared over 2k, remember? So when we play k equals 1 and q equals 1, we get a half. So there is one anyon of spin a half. Okay, so in this limit, we have we have an anyon of spin a half. In Chern-Simons theory, anyons are not physical particles, they're probe particles. They're Wilson lines. So we can think about this as a Wilson line of A naught. So they are introduced as auxiliary probe particles with infinite effective mass so that we can manipulate them at our will. But here the story is just a little bit more interesting because we have some high energy degrees of freedom, so to speak. The mass is very large, but phi is still a particle. It's a very heavy particle, which also has charge 1. So this Wilson loop now doesn't have to be infinite. It can end on phi. Right? Phi could be the endpoint of this Wilson loop since it has charge 1. A more physical way to say it is that this anion now should not be interpreted as a probe particle, but it's actually a heavy physical anion that you can excite from the vacuum. It's the phi particle. This is the phi particle. That sounds crazy because the phi particle is a boson. But now I'm saying that it becomes an anion, it becomes a spin and a half particle when you make measurements at long distances. How is this possible? That's exactly what I explained yesterday. Phi starts its life as an electric particle of charge 1. But then because of the Chern-Simons interaction, it becomes a little solenoid. So the phi particle starts as an electric particle, then it becomes a little solenoid. And because of this magnetic field that pierces through the particle phi, when you take this particle around itself, sorry, I meant a halfway, so that we're exchanging these two particles. When you exchange these two particles, you get a phase of -1. So an electric particle, a bosonic electric particle becomes a fermion. So the actual, if you make measurements in this theory at large positive m squared, you will see that there is a fermionic excitation, which is heavy. At mass, what is the mass of this anion? Let's see if you still follow. What is the mass of this physical anion? M, right. The mass is m. So in this theory, there is an actual excitation of mass m that is not bosonic, it's fermionic. It might seem bosonic in the Lagrangian, but because of the Chern-Simons term, it becomes fermionic when you replace it. So what is this? So the bottom line is that in this limit, the model has a fermion, a massive fermion. So this whole discussion here collapses to just the statement that in this limit, the model is a massive fermion. That's the law. That's the most interesting excitation. Because I chose the level to be 1, there are no other anyons. If I chose the level to be 2, there would be also anyons of spin a quarter. And the discussion will be more complicated. It's a much more interesting and confusing model if I took the level. But U1 level 1, it's very clear. There is one massive fermion. It's a familiar excitation. Okay, now let's analyze the other limit. Oh, it's a massive fermion, but we have to be slightly careful about the spin. You remember we have to distinguish a half from -1/2. So I'll take the spin to be a half in this convention. Okay, one has to be careful about the sign of the spin since we're in 2 + 1 dimensions. Yeah?
What is the trivial anion?
Trivial what?
Anion.
Oh, the trivial anion is nothing. It's an anion that has no braiding with anything, neither with itself. You're asking what kind of physical particle it could be? Well, for instance, it's a good question. For instance, Chern-Simons gauge field, the massive gauge field. You remember that this model has another excitation that I didn't even write, which is the massive Chern-Simons gauge field. It's a spin 1 excitation. It has no braiding with anything. It has no braiding with itself. You can think about this as a trivial anion. It has no braiding with anybody. Any other questions? Or you can think about the bound state of such two fermions as a trivial anion. That's also true. If you fuse two such fermions, you'll get a boson with no braiding. Yeah.
I don't know if it even makes sense in this case with the question, but I agree to the same. I mean, if I have some field in the Lagrange, the excitation does not transform with the spin of the field in the Lagrange, as in this case.
Yes.
This means that the vacuum is not going
No, it's just that the way we're taught quantum filter is incorrect. That's a better way to say it. This phi, what you said, let me just translate what you said into equations. What you said is that we have a vacuum. We act with phi on the vacuum. We create a particle. And what you just said is that phi is a boson. If the vacuum preserves Lorentz invariance, then the vacuum must be bosonic, and therefore the particle must be bosonic.
Yes.
This seems to lead to a contradiction, and the conclusion was that the vacuum is therefore not Lorentz invariant, and the whole thing makes no sense. However, that's not the way to think about it. This is not the way to think about it because the way you learn quantum filtering is misleading. Phi is not a good operator to act on the vacuum. Why? It's not gauge invariant. So we shouldn't discuss it. In fact, the vacuum here is fine. It's just that the simplest excitation, which you can think of as phi, becomes a fermion. The physical mechanism is that you create phi from the vacuum, then the Chern-Simons term comes in, pierces the particle with a magnetic field. In condensed matter, this piercing that I keep talking about is called flux attachment, which is a very intuitive term, right? Flux attachment. So it pierces the particle with magnetic field. And then due to the Aharonov-Bohm effect, when you take two phi particles and do this thing, you get a minus sign. And therefore, they should really be thought of as fermions. And when you second quantize the system, they will obey Fermi statistics, even though there are no fermions in the Lagrangian. Okay?
Can I have on vacuum with gauge invariant?
Yes.
Because I'm confused because in general, like it's quite a bit rare. We do that, for instance, with the immune.
Right. Yes, in the simplest examples that are taught in quantum filter courses and books, sometimes you would see this kind of imprecise discussions that people act with IMU or act with some non-gauge invariant operator.
Okay, so I can create, let's say, a photon with the IMU, and I write
well, you would.
Waves and then
Yeah, I know that. I know how this goes. Yeah, you start from IMU. You expand it in modes, and then you try to impose this BRST. There is a procedure that if you follow it, you get the correct answers, but you have to impose BRST. And actually, if you did it here, you would also get the right answer. This is not part of the BRST invariant Hilbert space. That's what you would find. When you would impose the BRST, you would need to add something else. And you'll eventually get the right answer, but you'll have to follow the procedure carefully. The BRST is essentially the same statement as saying that we only look at gauge invariant operators. What BRST says is that you start from the full Hilbert space, which is not physical, that includes also non-gauge invariant stuff, and you quotient it by gauge symmetry. That you look only at the gauge invariant sector of the Hilbert space. So when you follow this procedure carefully, you'll end up discussing the same things that you would get from acting with only gauge invariant operators from the first place. Okay? Okay, now let's discuss the other side of this phase diagram, which is large negative m squared. At large negative m squared, the gauge field is Higgsed because phi condenses. And you do not have to worry for now about the Chern-Simons term. So the gauge field is Higgsed. And the most important excitation in the Higgs phase, we discussed it in one of the previous sessions. That was, we write phi as absolute value of phi times the phase. And then we construct this object where sigma winds around. And this has finite energy because we also arrange for a gauge field that cancels the energy. So that's the magnetic vortex, right? That's what we call the magnetic vortex. It's a finite mass excitation in the Higgs phase in 2+1 dimensions. So here there are magnetic vortices on this side. And at this point, it's useful to say something, which I will not prove, but I'll give you a proof from a different point of view. So the construction of the magnetic vortex was that we write phi like that, then we let sigma wind around, and we cancel the energy from this term by arranging for the gauge field to cancel the energy in the winding of sigma. But now there is something new that did not exist before, which is that there is also a Chern-Simons term. And because there is a Chern-Simons term, the magnetic vortex that we constructed is not yet completely well defined. It's not gauge invariant, because of the same thing that I explained with monopole operators, that now this magnetic flux leads to some kind of integral over A, and this magnetic vortex is not yet gauge invariant. So we actually need to add another quanta of phi. We need to add some quanta of phi to make it gauge invariant, intuitively. I'll explain it more precisely in a second. So then you have a particle that's moving in the background of magnetic field, and this acquires half-integer spin. I'll give proof in a second from a different point of view. So the magnetic vortex here turns out to have spin minus a half, not plus a half. If you do the computation correctly, there is a minus sign. And it's massive. So the modification of the Chern-Simons term of the story that I told you before about magnetic vortices is that now the magnetic vortex acquired spin. And the magnetic vortex has now spin minus a half. It's a very nice exercise that you can try to do at home. Just you write the angular momentum operator, you write the magnetic vortex, and you will find that there is a contribution to the angular momentum from the Chern-Simons piece, which will make the angular momentum into a half rather than 0. Let me just give you a proof of this statement, and we'll go to a break. I want to give you a proof of this statement, and therefore make an argument that there must be a phase transition. I'll give you the proof here. So there are two ways in which you can prove that the magnetic vortices now acquire spin a half. One is by just doing the exercise I said, constructing them explicitly and computing the angular momentum. Another proof requires no computation, and no computation proof, so I prefer that one. And so magnetic vortices are actual physical particles, and they're created from the vacuum by acting with monopole operators. So monopole operators, when they act on the vacuum, create in the Higgs phase. That's always true in all theories in 2 + 1 dimensions. In the Higgs phase, they create magnetic vortices. Okay, that's the mantra. That's very important in supersymmetric theories and the mirror symmetry in string theory. That's the mantra. That to understand magnetic vortices, you can try to act with monopole operators on the vacuum in the Higgs phase. And now we do what this gentleman suggested. To compute the quantum numbers of this magnetic vortex, it's enough to compute the quantum numbers of this magnetic monopole operator, which is a local operator. And this can be done without any computation, actually. So you go back to this picture that you pluck a sphere out of space. That's the definition of the monopole operator. And you impose the flux to be 2 pi. And now what you do is that you recall that the gauge charge of the monopole operator is 1. So it's not gauge invariant by itself. So therefore, the monopole operator is not gauge invariant by itself. But here we have a dynamical particle phi that we can use to cancel that gauge non-invariance. So there is a gauge invariant operator in the theory, which is given by m phi star, actually. Okay. And this intuitively sounds a lot like the story I told you about the magnetic vortex, that you need to add another quanta of phi. Anyway, this is a good gauge invariant operator now, since this is the monopole operator. That's not gauge invariant. We multiplied by a massive, the massive particle phi. This is a good local operator. But this local operator is made out of a magnetic monopole and phi. What is the spin of such a system? Then you have a magnetic monopole and a scalar. This operator is actually fermionic. This is a fermionic operator. It has spin 1/2. So the magnetic monopole operator, the spin of the magnetic monopole, the spin of the monopole operator is 1/2. Minus 1/2 in this convention. Boom. So long story short, we have a funny phase diagram in which there is almost nothing going on. There is no symmetry breaking. It's not like the previous examples we studied. There is no superfluid transition. There are no massless degrees of freedom. On one side, there is a massive fermion with spin minus 1/2. And on the other side, there is a massive fermion with spin plus 1/2. But can it be that these are continuously connected? Can it be that you have a quantum field theory in two phases? In one, there is a fermion of spin 1/2, and on the other, there is a fermion of spin minus 1/2. Is it possible that these things would be continuously connected? The answer is no. It's not. There must be a phase transition. There must be a phase transition here. And now one has to guess what the phase transition is going to be. Which model do you know has a massive fermion on one side of the diagram and a massive fermion with the opposite spin on the other side of the phase diagram? Have you ever seen such a model before? A free fermion, right. So this theory, this whole thing is actually the same as just psi bar d psi. Sorry, no gauge interactions, just free fermion. So this has gauge fields, Chern-Simons terms, and a scalar, but it's actually dual to a fermion. Free, massless, free fermion. Now, let me just mention why, for those of you who have not seen this before. This is just a property of the Dirac of the free fermion. If we take the free fermion and add a mass, okay? When m is 0, the fermion is massless, gapless. So this is a gapless state, gapless second order transition. Second order transition. When the mass is positive, the fermion has two polarizations. The one comes down, and the one the mass is negative, the other comes down. So here the spin is 1/2 in some convention, and here the spin is minus 1/2. That's just the fact that the fermion has two states, and when the mass is positive, the Zeeman effect picks one, and when the mass is negative, the Zeeman effect picks the other one. That's just a property of the free fermion. And that phase diagram looks very much like this. So people were compelled to conjecture that this is just a massless fermion. So this is the simplest boson-fermion duality. Boson-fermion duality. On one side, we have U1 gauge theory with a boson at level 1. And on the other side, we just have a fermion. That's an important duality in condensed matter. It arose in various ways in condensed matter systems, and then it found its way to particle physics, which also had many applications. And that's already quite recent.
You speak about the Zeeman effect because the mass plays the same role as an effect.
Yeah, if you just quantize the free fermion, you write the Hamiltonian, then the mass in the Hamiltonian looks like this. So without the mass, there are two states, and with the mass, you either pick the spin up or the spin down. The spin up in this convention has to do with what you would call spin a half excitation in 2 plus 1 dimensions, and spin minus a half. So this is a very surprising example of a system that's made out of bosons and gauge fields, but it's actually just a free fermion in disguise. And actually for this one there is experimental evidence, as well as some lattice simulations, Hamiltonian truncations. People are trying to prove that. It seems very compelling. It's not proven yet, and there is some evidence that this is true. Yeah?
This is somehow related to the US amino type dualities, where there are free fermion stuff, this dual 2 stuff, level K.
Right, so you're asking if this is connected to the boson-fermion dualities in 1 plus 1. What you're talking about are 1 plus 1 dimensional boson-fermion dualities that you can read about in Polchinski's books, for instance, on string theory. Whether or not this is related is an open question, in my opinion. Nobody has made a connection, as far as I know. Maybe somebody in the audience knows otherwise, but I've never seen a connection being made. Oh, except I want to say one thing. Sorry, I interrupted you. There was one attempt to make a connection. So the idea is the following. You start from 2-dimensional space, which is a half infinite, with a boundary, which is 1 plus 1 dimensional. So you study 2 such half infinite spaces. And in the bulk of this 2 plus 1, of this 2-dimensional space, this duality holds. So the idea is that it therefore has to induce some kind of duality on the interface, on the boundary. And loosely speaking, it looks like you induce a more or less standard bosonization duality in 1 plus 1 dimensions on the boundary. So that's perhaps a connection. But it's extremely not obvious that this is true because you have the boundary conditions map in a funny way. Dirichlet boundary conditions on one side map to Neumann boundary conditions on the other side, and typically. Any other questions before the break? Yes.
So for the 4-dimensional, just something I was thinking about, for the 4-dimensional extension, so you change signs where you consider a sensitivity where they effectively have a prefix in front of the A, which A. I was just wondering, would that then give you an idea about the vacuum?
Which model are you talking about?
So Castello.
Stello?
Castello, Kevin Castello.
Oh, yeah. You're talking about the what they call holomorphic Chern-Simons theory in 3 plus 1 dimensions? Yes. What about it?
So, I mean, with an extra factor in front of the HHA, so I'm wondering if that would tell you a little bit about the vacuum that the particle is moving around.
What you're asking about is an extension of the Chern-Simons Lagrangian to 3 plus 1 dimensions, which looks like you pick a 1 form, and then you do wedge A, wedge dA. That story is actually not a true 3 plus 1 dimensional field theory because you have to pick a 1 form.
Yeah.
So however you do that, you are going to break Lorentz invariance in 3 plus 1 dimensions. It's really a 2 plus 1 dimensional Chern-Simons theory. The way to think about it is that it's a 2 plus 1 dimensional Chern-Simons theory, maybe on something like stacked, like a grid, like something like that. But it's not truly a 3 plus 1 dimensional field theory because it's not Lorentz invariant.
Okay, so it wouldn't give any other intuitive ideas?
You're asking perhaps if people try to extend these things to this mark that I've never seen people trying to do. Any other questions? Okay, so we'll resume after the break. Okay. Any more questions? Yes.
Can you drop in your argument? Can you drop F squared there?
You're asking if it's possible to drop the F-mu square term here? Yes. Yes. You're asking if it would give the same answer?
Yes.
Yes, it would. That's not always true, by the way. That's not always true. There are examples where it doesn't give the same answer, but here it does. Any other questions? Okay, so the last thing, there is one more concept that I wanted you to know. That's my last planned concept that I wanted to teach you. So we discussed the bosons coupled to Chern-Simons terms, but I wanted to tell you about what happens when fermion. So really, if you think about the examples that we covered, we had the which examples did we really study in this course so far, right? Let's just summarize. We studied many examples, and each example had some different new thing that we learned from it. Let me just summarize these examples, and then I'll explain what is the next example that we need to study, just to complete all the possibilities. So first, we studied the O2 model. Well, we studied the Ising model. First, we studied the Ising model, just phi to the 4. So this was d phi squared plus phi to the 4. Then we studied the O2 model. So there were no gauge fields thus far. This was the O2 model. Then we studied U1 gauge theory with a scalar. That was f squared plus d phi squared plus phi to the 4. Then we studied a free fermion. We studied the free fermion. And finally, we studied U1 level 1 with the boson. So it's this guy with 1 over 4 pi ADA plus d phi squared plus phi to the 4. So each model had some different new thing that we learned from it. So there was a duality here. Remember? Then there was a duality here, boson-fermion. So this was a boson-boson duality that showed that gauge. Okay. This was a boson-boson duality from which we learned about particle-vortex duality, that particles and vortices are indistinguishable. That was one lesson, that sometimes they're indistinguishable, particles and vortices. That we'll also learn the notion of infrared duality from this. And actually, there is one more thing that I didn't emphasize that this duality teaches us, which is very important, which is that gauge symmetry is fake. I didn't say that, but gauge symmetry is a fake thing. Because here it's fake, because you see that one side has a gauge field, and the other side doesn't have a gauge field. So there is nothing fundamental about gauge fields. They can go and come. You've seen that also in Napadal's lectures, I believe. He must have taught you Seiberg duality. But that's much simpler. You see that the gauge fields are fake. From these examples, we learned about Chern-Simons, about boson-fermion duality, that bosons and fermions are indistinguishable. So basically here you learn that gauge fields are fake. Here you learn that statistics is fake. So everything's fake. So bosons can transmute to fermions, gauge fields can disappear, everything goes. There is one thing that's conspicuously missing from this list, which I've avoided so far, which is fermions coupled to gauge fields. What happens when you couple fermions to gauge fields? That has a completely new ingredient that I haven't taught you so far. And that's what I want to teach, the last thing. And we'll discuss this model. The simplest, that's the quantum electrodynamics. The simplest version of quantum electrodynamics in 2+1 dimensions. So that's sometimes called, the model that I will teach you is called QED½ in 2+1 dimensions. You'll see why it's called, I'll explain soon why it's called QED½. There are several versions of QED yeah. So that's the last thing that I wanted to cover. And just to ruin the surprise, this will turn out to be dual to this. So fermions are fakes, gauge fields is fake, everything goes. So that turns out to be the same as this. So But to understand how that works, one needs to learn a new concept. The concept is of decoupling in quantum field theory. The notion of decoupling in quantum field theory is this idea that if you have a particle, or a particle whose mass is very large or even goes to infinity, you can ask, what does it do for infrared physics? What does a heavy particle can do? What does a heavy particle do for infrared physics? And typically the answer is that just common sense tells you that it doesn't do anything. Okay. That's the common sense answer, and it's mostly correct. In most examples, it's correct. But there are some examples where the story is a little bit more complicated. The most famous example is actually from the standard model of particle physics. That's maybe the example that you all know, which is the issue with the Higgs mass. You must have seen it before, that there is a question that is called the hierarchy problem. Did you hear about it? What is the hierarchy problem? The hierarchy problem is nothing more than the statement that if there is some extremely heavy particle, let's say a black hole or a string, something extremely heavy, and you just compute this diagram for the Higgs mass, then you find that the mass of the Higgs, is sensitive to the mass of this new physics particle. So that raises a question of naturality for the standard model, that there is some hidden conspiracy that somehow makes all these things cancel out. And of course, this is one of the reasons that people invented supersymmetry in the connection with the particle physics. Because when you have supersymmetry, the new physics particles come in supersymmetric multiplets. And for every new physics particle, there is another new physics particle that comes with the negative sign. And they all cancel out. So people invented lots of ways. Another thing that people invented to overcome this problem is the idea that the Higgs particle is not fundamental, that it's composite. If it's composite, then this diagram doesn't make sense at high energies, and you need to replace this diagram by something else, and this goes away. Another thing that people invented to overcome this problem is extra dimensions, which also gets rid of this diagram at high energies. So little Higgs models is something that people invented to get rid of this. So there was a series of inventions in the mechanisms in particle physics to ameliorate this problem. That's an example where something heavy doesn't quite decouple. It leads to some confusion for why something is light, why it's not heavy. So I'm going to tell you about a similar thing that happens in 2+1 dimensions. It's a certain non-decoupling phenomenon. So it happens when you have fermions coupled to gauge fields. So you just, let's say, start from some Lagrangian. You start from some Lagrangian. I'm writing it now very schematically, as you see. You start from some Lagrangian like this, and you add a fermion that has a covariant derivative, just minimal coupling. And you add a mass. You ask, what does this do when the mass goes to infinity? Does it decouple or does it not decouple? Okay, you try to decouple the fermion. You can take it to plus infinity, or you can take it to minus infinity. The mass is a real parameter here. The mass is a real parameter for a single Dirac fermion. So plus infinity and minus infinity may not be the same. So if there is a non-decoupling effect, you have to worry about whether it's plus infinity or minus infinity. Because it's a real parameter, it might not be the same. So the question is, what does it do? Whether it really decouples or doesn't decouple. So people have, there is a one loop diagram where you put a mu on the external legs and a nu in the internal legs, and then you run the massive fermion in the loop. There is such a diagram that you can compute. It was first computed by 3 people, Redlich, Zemenov, and Niemi. They computed this diagram first and gave an interpretation of the result. And what they found is that this diagram is given by some integral, and it contributes to the polarization tensor of a nu, right? And what they found is that when you take the mass to infinity, almost everything goes away. So they found that basically almost everything goes away. Like this diagram just goes to 0, except for one term. Almost everything just goes to 0, as you expect from decoupling. The diagram goes to 0 when the mass is infinite. So almost goes to 0, except for one piece, which turns out, so one piece in pi minus survives. And this piece has the following behavior. It depends only on the sign of the mass. So the way it comes out from the actual computation is the mass divided by the absolute value of the mass. That's what you find from the integral. Times epsilon mu nu rho. And then you have the momentum, p rho. So this is a function of momentum, as you always do with the vacuum polarization. So this is the only piece that doesn't go away. Everything else is order 1 over the mass. So it goes away in the infinite mass limit. Okay, so that's the precise answer, up to some 4 pi's that I'm not putting. What is the interpretation of this answer? The interpretation of this answer is that since this is one factor of momentum, it's like a one derivative term. And since there is an epsilon tensor, it fits this guy. So it renormalizes K. This is a renormalization or shift. I don't like this word, so I'll just use shift of K. If you work out the coefficients, it takes K to K plus the sign of the mass. A half. This half is going to be super important. Okay, so it takes K to K plus a half of the sign of the mass. So in the original Lagrangian, when you write it, let's say you put it on the lattice, you just write the ultraviolet Lagrangian, there is some K. This is called K bare. This is not what, well, let's call it KUV. KUV. Bare is used sometimes for something else. So the K that appears in the ultraviolet Lagrangian is let's say KUV, K ultraviolet. And now, because of this effect, when the mass of the fermion is very large, the actual K that you measure at long distances is not KUV. When the mass is very large and positive, the K that you would measure at long distances is given by KUV plus a half. And when the mass is very big and negative, the K that you would measure is KUV minus a half. These formulas are all extremely confusing, and they've been very confusing when people discover these things, because the whole idea is that K is an integer. What does the half have to do with it? So, but K has to be an integer. So what's going on? The way to think about it is that the requirement that K is an integer comes from analyzing the gauge invariance of this piece. But the idea is that there is something about the fermion that also contributes to K, this loop. And so the thing that you should really impose to be an integer is the K that you measure at long distances. Because the K that you measure at long distances is what determines the topological field theory. The topological field theory at long distances is determined by K infrared, not KUV. And therefore, this has to be an integer. This must be an integer. So therefore, KUV is allowed to be a half integer. So KUV, in fact, not only it's allowed to, it must be a half integer. Because otherwise, K infrared would not be an integer. So KUV must be a half plus some integer. Otherwise, the theorem makes no sense. This might strike you as odd, but yeah, when you write the Lagrangian in the UV, you put a half integer. And that's okay. It doesn't violate gauge invariance because there is still a fermion in the Lagrangian. When you remove the fermion, integrate it out, it would shift properly and it will be an integer. Is that okay? That might be a very bothersome point to you. And there's a huge discussion about it in the literature. There are some people here that work on this stuff. They can tell you how much confusion this causes in the literature, right? I see some people are nodding. But that's the way it works. You should always insist that the K at long distances, which describes the topological field theory, is an integer. And then you're on safe grounds. Whether or not the K that you write in the ultraviolet Lagrangian is integer or not is a little bit ambiguous. So that's why the simplest example is called QED a half. Because the simplest example, the simplest theory, in the simplest example, KUV is chosen to be a half. That's the simplest analog of electrodynamics in 2+1 dimensions, where KUV is chosen to be a half, and that's called, sometimes people call this model U1 plus psi, or QED a half, or QED half, QED3 half. Yeah, there's like I saw this notation sometimes, but this is more common. This is a more common notation. U1 plus psi. Okay. Is this discussion clear, or it's very confusing? Yeah.
People sometimes think in terms of a polymerized regulator, and then there is an extra half.
Yeah, I told you that this is really a marsh of confusions. One convention. I don't want to confuse you even further, but indeed, when you put Pauli-Villars fermions, then they also shift K. Because you put back more fermions, and every fermion you put, this one loop diagram just adds up. So every more fermion you put, it adds up. So you have to be very careful with these conventions. And the bottom line of this, the bottom line is that you should always insist that K at long distances, below all the fermion masses, is integer. And then you know that you have a well-defined topological field theory with finitely many anyons. If your infrared K is not integer, then you're in trouble. The rest of how you write the Lagrangian, how you regulate it, it's something you have to do it like, you just have to close the door and do it quietly and not tell anybody. And then like when you get the physical results, that's what matters. The conventions are all over the place and they're very confusing. And there are also big differences in the conventions between condensed matter people and high energy people, which causes also a lot of confusion. It's because this shift is kind of a messy thing, and okay, so let's study this model now. So we're going to study this model, and for the good, I mean, you can also add f squared, but as Andrea said, it's not really going to change much. But I'm going to add it though, because it will be kind of useful to do it. And we've taken KUV to be a half, as I wrote above. So let's try to understand this model. So now we have all the tools to understand this model. We understand monopole operators. We understand the phases of U1 gauge theory. So we are ready to tackle this example. Are there any questions before I do that? I have 20 minutes. I'll finish this example, and then we can discuss whatever you want. So now this phase diagram is a function of m, not m squared. And again, it's a very interesting thing to study. There are all these things that we've seen before come to play again, a little bit more complicated because there are fermions now. So at very large positive M, the first thing that you must recall is that K of the topological filter, which determines how much solenoid sticks out of particles, is half plus a half. So here K infrared is 1. So the low energy effective theory is AdA with a quarter, with 1 over 4 pi. So there are no massless photons. There is a Chern-Simons mass. There is a so the mass of there are no massless photons. That's the first conclusion. There are no massless photons. The photon has acquired a mass from the Chern-Simons interaction here. So there is a massive spin 1 photon, a Chern-Simons photon. So we have the same discussion that we just had in the previous hour. This theory has how many anyons? Let's see if we still remember. 2. There is 1 trivial anyon and 1 anyon of spin a half. 1 anyon of spin a half. And as before, this anyon of spin a half, what is it? Now there is an obvious interpretation what this particle is. Previously it was the boson through which some solenoid was piercing. And now this is just the fermion psi. So the anyon here has an obvious interpretation. It's just the original fermion. There is no transmutation of the statistics. The ultraviolet is a half. By the time you go to the infrared, this spin a half particle is nothing but the fermion. Yes?
Why is there not the similar mechanism where the fermions act as point charges that have the same flux attachment?
Right, because this for bosons it was a little bit easier because you could think about creating the boson, and then there is a Chern-Simons term, so it would add this thing. But here the Chern-Simons term and the fermion are not completely independent things, because the fermion shifts the Chern-Simons level. So what you know for sure is from this, you go to the way to not make a mistake and not get confused. You go to the infrared, you compute the spin of the anyon. There is an anyon of spin a half. That means that there is a massive excitation in the system with spin a half. That's it. So there is a massive fermion. And in that way, you never get confused with flux. Flux attachments for fermions is kind of a tricky thing because the fermions themselves shift K. So how much flux is attached is a little bit a complicated thing. But the way to never get confused is to go to the deep infrared and read out the spins of the anyons, because that's what you would see when you do this experiment. That's what you will see. So that's the actual state there is a state in the Hilbert space like that. The most important thing that I'll need for the rest of the discussion is that there are no massless particles. In fact, for this example, we will only need this. No massless particles. That's the only thing that you need to know about this phase. there will be some phase transition. Next, so what is the K infrared at huge negative mass? This is going to be a half minus a half. So here, this is the more interesting phase. This is 0. And now everything that you've learned should come back. What happens when we have F mu squared and no K? What's the effect? How is this effective filter called? What is the effective filter with 0K? What happens when K is 0? Yeah, it's just a photon. And what is this? Is this gapless or gapped? Is this gapless or gapped? Gapless. This is the superfluid. So in this phase, there is a S1 worth of vacua. Here there is one vacuum. And here there is an S1 worth of vacua. Another interesting question here is about the monopole operator. The monopole operator, now instead of being dressed by a boson, as before, we dress it by a fermion to make it gauge invariant. So there is a half unit of angular momentum in the spin, and another half unit of angular momentum because of the microscopic fermion. So this operator is now bosonic. This is a bosonic operator now. And so we now have a bosonic order parameter. We have a superfluid phase and a trivial phase. Therefore, we are compelled to identify it with the phi order parameter in the O2 model. It's the exact same phase transition. This operator is going to be dual to that operator. This condenses in this phase. This is the trivial phase. And it's essentially the same phase diagram as before. So let's see. What else should I say about this example? There is a question here that you might be confused about. That's a remark that I want to make about this example, which is that there is an energy here of spin a half. So there is some kind of probe particle that will have half-integer statistics when they cross each other. So the picture is going to be that this replaces places with this. You might ask, how come there will be such a thing in the superfluid phase? Actually, nobody worked it out in the literature, but there is no immediate contradiction. The reason being that this anion is a probe particle. It's a heavy spin a half. It's just it's a heavy probe particle, so it's described by a Wilson loop. So it should be possible on the superfluid side of this duality to construct a certain defect operator that would also have effectively spin a half. But this was not done, as far as I know. However, many things work out. So first of all, the phases agree. There is a gapless phase, there is a gapped phase. The operators agree. The spectrum of local operators, as far as we can say, is the same. This operator is a bosonic operator. It should be dual to phi. The symmetries agree. There is a magnetic symmetry on this side of the duality and O2 symmetry on this side of the duality. The particle excitations that we can see agree. So this duality has a huge amount of evidence playing for it. But there are some questions about the Wilson lines that are not yet addressed in the literature. The mapping of the Wilson lines is not yet completely resolved. Nobody worked it out. I should say that in some supersymmetric examples which generalize this is understood. The mapping of the Wilson lines was understood. So perhaps a similar technique would apply here, but I don't think anybody looked at it yet. So, just to finish. Yes?
I don't see how in the OT model you have the inefficient right, the spin 100.
Okay, let me explain it again. I just want to convince you that there is no contradiction with the particle spectrum, but there is an open question about Wilson lines. So let me explain this example again. So in the positive mass side of this correspondence, of this phase diagram, what did we see? We saw an anion of spin 1/2. That's what we saw. That means that there is some object. It might be a dynamical particle, or it might be a probe particle, which behaves like a fermion. We have to decide if it's a probe particle or a dynamical particle. That's very important, because if it's a dynamical particle, it's in the Hilbert space, and there should be a corresponding particle in the Hilbert space of the superfluid. And that would be a contradiction, because there is no fermions in the Hilbert space of the superfluid. It's a bosonic model. So I have to try to give you some sort of evidence that this may not be in the Hilbert space. Because Chern-Simons theory doesn't know about what are the massive particles. Chern-Simons theory is the low energy approximation, which tells you what are the possible anyons in the system. It tells you essentially about what is the topology in the ground state, which anyons does it allow. But it does not tell you which anyons have a finite energy in the Hilbert space, which anyons can actually be excited with a finite energy investment. Okay? So there is no immediate contradiction yet. And the way it goes, the way I imagine it goes is the following. So we know that the Chern-Simons predicts that there is such an anion. But there is another thing. There is a fermion which has charge 1 and spin 1/2. So what I imagine is that the particle that actually exists in the Hilbert space and has finite mass is when you take this thing and you stack a fermion on it. Then it becomes bosonic. But the object without the fermion would not be in the Hilbert space. That's a possible way it could go. Yeah, that's a possible way it could go. There is some hint that this is indeed true, because when you construct the monopole operator in this phase, it looks like this. And this is a bosonic operator, which is identified with phi under the duality. So the Chern-Simons theory tells you which anyons could exist, but it doesn't tell you which ones exist as finite energy excitations in the Hilbert space. And I think what it tells you is that there is a probe particle which could carry spin 1/2, but it's not in the Hilbert space. The thing in the Hilbert space would be a composite of this with a fermion. And so then the problem becomes a little bit less severe. It just means that you have to find the Wilson line on the bosonic side that has a spin 1/2. And this is perfectly plausible. Because once you add probe particles, you can put whatever spin you want on the world line. In the context of supersymmetric duality, there is a very nice work by, I think, is it Ishtiak? It's Gomis and possibly Ishtiak, but I don't remember, Gomis et al., about the mapping of Wilson lines to vortices. And that's essentially what we do. In the context of supersymmetric theory, they show that you can map these things properly to each other. And you have to be very careful about distinguishing the Hilbert space excitations from probe particles. And so I think that this will be this is not a contradiction. This duality is believed by everybody to be correct. Everything works out. All the operators map, the symmetries map, the phases map, and that's it. Any other questions about this? Whatever you can now ask. We have 10 minutes. You can ask whatever you want. So it doesn't have to be even intimately related to this course. So if there are any questions, I'm happy to take them now. Yes?
I just popped out before when Mario asked about Thermionic ground state and blah blah blah. Well, why should be a problem with Thermionic ground state? I'm confused because right when, for example, with the indices, make a difference between Thermionic and bosonic ground states. Because the ground states one is Thermionic.
Okay, I understand the question. You're asking, I assume throughout this course that the vacua in quantum field theory are Poincare invariant and Lorentz invariant. So that means that P annihilates this vacua. They're translationally invariant. And they have zero angular momentum. So the angular momentum is zero. Zero. Okay, I assume this throughout the course. What you're asking about is disconnected from what I discussed. You're asking about what the hell are people talking about when they're talking about fermionic ground states.
Yes, exactly.
So the setup there is the following. Suppose you have a QFT with a unique translationally invariant, completely Poincare invariant ground state. Let's call it the vacuum, but it's gapless. So you have a fermion, a massless fermion. It doesn't matter in how many dimensions it is, but if you want to be concrete, we can do 1 plus 1, massless fermion in 1 plus 1 dimensions. Now, you can ask, what happens if I, instead of, this is true in R1, 1. You can think about it anything. So in R, 1, the statement would be that there is a gapless, massless fermion, and a unique vacuum. Now, there is something interesting that happens when you put the theory in S1 times time. So instead of studying the theory in infinite space, you study it on a circle. Now, you have to expand these fermions in modes. And you have to make a decision of whether you are going to look at what's called the Neveu-Schwarz sector or the Ramond sector, which I think Kostas must have mentioned. So I'll choose a convention where psi is periodic. That's what Kostas probably called the Ramond sector, right? So that's what people typically call the Ramond sector. So if you assume that psi is periodic, and you quantize on S1 times time, then there is a zero mode for psi. So there is one zero mode for psi plus, and there is one zero mode for psi minus. And I'll take these fermions to be Majorana. So there is no just transpose. Okay. So there are two zero modes, and you get quantum mechanics for the zero modes, because now you just you assume the fermions are independent of S1 at this point, and you just get quantum mechanics. And this is quantum mechanics of a single complex fermion. Okay. Now, why is this fermion complex in quantum mechanics? It started its life as a real fermion in 1 plus 1, Majorana, but there were two of them. So they become one complex in quantum mechanics. Now you have to quantize this system in quantum mechanics. In quantum mechanics, you would say that psi bar and psi give 1. And you construct an annihilation operator by combining them in the usual way. You construct an annihilation and creation operators by combining by essentially using psi and psi bar. Therefore, this quantum mechanical model therefore has two states. One state you call your name, let's say Zohar, and the other state you call psi dagger Z. So there are two states. It makes no sense to discuss which is the vacuum. This theory has two ground states on the circle. And symmetry in the system is -1 to the fermion number. So this ground state has +1 in some convention, this has -1. It's also up to you to decide which ground state you should call fermionic and which ground state you should call bosonic, because you can call this bosonic and this fermionic, it doesn't matter. In fact, the two choices are related by transformation. This transformation now has a name in the literature. I'm just saying that if you want to learn about it. It's called Topological Fermionic Invertible Model. Something like this. This is like which you call bosonic, which you call fermionic. It's up to you. But whatever you decide, one will be bosonic, one will be fermionic. But this has nothing to do with the ground state of the theory in R11. You see? One ground state in R11, a gapless fermion. This leads to two ground states on the circle in the Ramond sector. If you chose the Navier-Schwarz sector, we're just one. This is an artifact of compact space. In compact space, you use Poincare invariants, and you can have several ground states. And the number of ground states depends on the boundary conditions. For Navier-Schwarz, you have one ground state. For Ramond, you have two. One you may call fermionic, one you may not call fermionic. This is TIFO or TIFI? I don't know, topological fermion. Maybe some. I don't remember if this is called. Yeah. But this transformation was explained in a very nice recent paper by Shao, Wen. This is a condensed matter paper, and others. They realize this transformation is important for something of who you call fermionic, who you call bosonic. Yeah.
How much of our analysis carries through to the non-abelian sign theory?
Most of the things I said apply. Of course, the braiding and fusion is much more complicated. The anyons are more complicated. To compute their spins is much more complicated. But the idea that K shifts applies. The basic way of analyzing the phases applies. A lot of it applies. Yeah, so there is a huge, huge literature on boson-fermion dualities in non-abelian gauge theories. I just gave you probably 3 or 4 examples in abelian gauge theories, but there is a huge literature on the non-abelian case.
Okay, and the last one is that in non-abelian we have some interpretation in terms of topological string.
What is?
Like a Komargodski duality and so on. For example, Simon and string, you can see as, I don't remember if open string on the star of a string. Maybe there was a 2B dual. So I have this geometric counterpart in that case. Is there something similar for abelian case? Abelian Schoenstein?
That's the more interesting question is probably if you can add matter, because that story that you just mentioned is for pure Chern-Simons.
Yes.
The dualities are not for pure Chern-Simons. The dualities that we've exposed have dynamical matter fields. Okay? And once you have dynamical matter fields, the duality of Gopa-Komar-Vafa is not true anymore, but there are generalizations of it. So if you're interested in the supersymmetric constructions, there is a sophisticated generalization of this kind of correspondence, which is called 3D correspondence. That's like a geometric machine. It's a geometric machine that connects topology of 3 manifolds. This is called 3D duality. 3D correspondence. And it's been worked out by people like Dimofte. He has written many papers about it. So the idea is that one side is Chern-Simons matter theory, and the other side is some question about topology of 3 manifolds. And it's kind of in the same ballpark. And you can derive 3D dualities for supersymmetric theories from some properties of 3 manifolds. This is just for supersymmetry. There is no such thing. There is no such organizing principle for the non-supersymmetric dualities that I talked about. Nobody has such an organizing principle. Just for supersymmetry, there are these connections to topology. Yeah.
Yesterday we said that an experiment can measure spin up to
1, 1. What do you say?
Experiments can measure spin up to.
Long distance experiments. Well, of course you can measure the spin of a particle in an experiment, but the long distance observable, when the long distance observable measures the Aronoff bomb, maybe I haven't said it right. Of course, if you have a chunk of stuff in an experiment, you can measure its spin. What I meant to say is that if you perform truly low energy experiments, like these braiding phases, then you will not have access to the full spin. You'll only have access to spin mod 1. Because you can tack on these little anyons, particles in the Hilbert space of spin 1, for instance. and change their spin while not changing any of the topological properties.
Why don't you do it over there when you have this minus half and half, and say that or even left side is also spin half?
Yeah, you're asking of how did I distinguish this from that?
Yes.
Yeah, so this is in principle a very good question. So here, basically what you say is that there is a massive magnetic vortex of spin minus a half that you can construct, and it seems like the lowest energy particle with that spin. But it's true that in the same sector of magnetic vortices with the exact same magnetic flux, you can also construct a spin a half magnetic vortex. Yeah, plus a half. It is true that it's true. What you say is true. For instance, you can just take this local operator m phi star and multiply it by f mu nu. Then you have an operator of spin plus a half. Well, local operators are classified by SU2 anyway. The spin of local operators. Here I said something imprecise. The spin of local operators is anyway classified by SU2, not U1, because the local operator is a point in R3. So the spin is SU2. The spin is a half. Now you can act with this operator in the vacuum. You will get some state. It could be a state of spin a half or minus a half, because the states are actually classified by U1. That's a dynamical question of what do you get. You get a half or minus a half. And of course, you can take this particle and tack on this particle electromagnetic wave, and you could change the spin. The statement here is really that there is such a fermion in the spectrum. There is a fermion of spin minus a half in the spectrum. And it's the lowest lying vortex has this property. Yeah?
You didn't speak of fermion duality.
I did not speak of that, correct. Yeah, I don't. Lack of time. I don't think that fermion dualities have new ingredients. I chose the examples in such a way that every example has something new, like some new idea or a new concept. The fermion dualities, I don't think have a new. I don't believe they have a new ingredient. There is one ingredient that I never discussed. I did not discuss dualities which have a genuine topological phase and level rank duality. That's a conceptual thing that I did not discuss. There is some ingredient there that did not exist in any of the examples. But the abelian Chern-Simons, the abelian fermion dualities don't have, the simplest one doesn't have this issue. So it doesn't, yeah, it wouldn't give a new thing to study. Any other questions? Yes? A duality between, such a duality is, for instance, ADS-CFT. This is a duality between different theories that live in different dimensions, but typically such dualities involve gravity. Involve gravity, because gravity is holographic. It's there is something that reduces the number of effective dimensions in gravity. Without gravity, duality between field theories in different dimensions. Well, one example was mentioned here. That's for topological filters. So in the context of topological filters, because it's again, topological filters live in 2+1, but they don't have degrees of freedom in 2+1. Okay? So they can be dual to something that lives in lower dimensions. Okay? That can in principle happen when you have no degrees of freedom. And so there is a vast literature on the duality between Chern-Simons theories and Wess-Zumino-Witten models in 1+1. So there could be dualities across dimensions, but in quantum field theory, this typically means that at least one side doesn't have degrees of freedom. But otherwise, you need gravity, maybe. Yeah. Any other questions? No last question? Okay. So we can finish now. Okay.